its elements. Okay, so heat of formation means forming 1 mole of a substance from its elements. Generally, it's called standard heat of formation. What does the standard mean?
Room temperature.
So room temperature, which is 25 degrees Celsius or 298 Kelvin. What else does that standard mean?
1 atmosphere.
1 atmosphere and 1 molar solutions if we had solutions. So anyway, William, give me a compound. Let's form one. Lame. Okay, sodium chloride. All right, sodium chloride. In what state of matter is it at room temperature? It's a solid. Okay, and we're going to form 1 mole of it from its elements. What are its elements? Can you tell me how to write that? 1 Na solid plus. How do I write that? Just Cl? That's not an element.
Oh, it's not.
Yes, it's in its elemental state, which is the molecular form. Wonderful. Okay, so solid sodium plus half a chlorine gas molecule yields 1 sodium chloride. This delta H, not F. Delta H in formation, standard conditions. It probably releases energy like, I don't know, negative 500 kilojoules. I sometimes make this up, but it's close. Okay. Megan, give me one. Let's get crazy. Let's get something better than sodium chloride. Ammonium dichromate, what'd you say? Okay. No, it's only 2, it's like 3. We could do that. Okay. Cyanic acid. I was trying to go bigger and better. Go ahead.
Well, you have to have some
Mm-hmm. Mm-hmm.
And then we need some diatomic gas.
Okay. Okay.
And then probably some carbon.
Just straight carbon, all right. And straight carbon is just solid. Got it. Oh yeah, because carbon. Okay, so carbon is a nonmetal, but it's one of those that are actually not usually gaseous unless it's in a compound form, like methane or something. So it's generally solid room temperature, like graphite that you're writing with right now. Okay. All right, and then we form that, and that's probably a negative, like. Sure, I don't know. It's going to be close to that. We will have a huge table on the back of our. In the back of 1 second. In the back of our textbook, like appendix 1. Appendix 1. So there's you guys have a textbook, you can do that. Some values in it, appendix something. Okay. So there's a huge table, and it's in alpha order, and it tells you, or actually it's not order based on the elements, it tells you like all the magnesia compounds, all the hydrogen compounds, the lithium compounds. It tells you all their delta HFs, the delta H formation. So if you ever need a value and I don't give it to you, it's probably because it's in here. Okay, question?
Can you use the 22.4 conversion when you're doing like this standard?
No, because that's STP, which is, what's STP conditions? 273 Kelvin, and this is not. So that's one of the kind of misnomers. We say standard temperature and pressure. This is standard conditions, where STP is standard temperature and pressure. This word standard is common, but it's not the same. Okay. If it's it'll say standard conditions, like at standard conditions, or at STP. It won't just say standard. Okay. I just want to do one more of these just to verify you guys could write these out. Ooh, that's the next slide. Actually, okay. So take a second and write down the vaporization of water and fusion of water, including the standard enthalpy value for that. Hopefully it takes you like 30 seconds. And you have your homework out for me because we're going to try a couple of those shortly. I won't wait till the end of the lecture, but I can I'll come up with some of those. The values are on the board. The values are on the board. You shouldn't have to listen. All right, Quee, help me out in the first one. So I actually want you to write the thermocouple equation for this. because I already have the value, like I already got that, right? But I want you to write the equation so I can put the delta HF at the end, or the delta H VAT at the end. H2O liquid forms H2O gas, right? Pretty simple. And then what do we put here at the end? Okay, 43.99 kilojoules, and that's per mole. And this is at standard. So how do I include standard on my H? Will not, and this is vaporization, so the HVAP just kind of signals that. So pretty simple, yeah. So this one doesn't say enthalpy of formation. So it has to say enthalpy of formation or heat of formation to say, okay, form one compound or one mole of compound from its elements. So this is just telling you to vaporize the substance, that's it. So Jason, how about the last one? Solid, right? Because we're going to then, what does this mean right here? What does it mean? I hear a lot of people saying solid liquid, but what's fusion mean in general? Which phase change? I hear melting. Okay, so this means to melt. So we're going from solid, keep moving. Okay. And delta H, what here? Fusion, not, equals. There you go. That's it. So don't be afraid to like really, when you're reading, don't just think formation all the time, but kind of look and see what it's talking about, and then you're good to move on. Okay. All right. So let's
So you won't actually have to memorize the delta H values for fusion.
No, you won't. You'll be given them a lot, but I actually like to tell you them up front because you see the difference between the magnitude of these values, which would indicate like how much energy it takes to separate, solid from solid and liquid from liquid to form a gas. Okay. All right. So this right here is my key to life. This is the information that I think is most important with the Kugels and MCAT stuff. The only thing that a lot of people have some issues with is figuring out when do I add masses and when do I not. So as you start to approach more questions, this is going to be like my tips for you, okay? We have a solution process, and this is like we had in our lab, which I saw a lot of you guys finishing editing that, thank you. When you have a solution process, so like salt and water, you're going to add up your total mass of solid and liquid water. But our C is usually assumed to be C for water, so specific heat capacity for water. Now, that's why, because we truly have a different specific heat capacity, but we use it out of convenience and because most of our solutions are really, really dilute, okay? And then, this is a little scribbly, but delta H, whenever you're finding the heat of solution for this, remember it's always Q of the solution process or Q of reaction, which really, these terms right here don't necessarily matter as long as you know what you're talking about, but the Q for the total process divided by the moles of solid. So this says moles of solid here. The board has a mind of its own. Okay. Not moles of water, because we're talking about the process of the solution being formed from the ionization or the dissociation or the dissolution of the salt. The next style is when we have acids and bases coming together, like a liquid aqueous solution of an acid, liquid aqueous solution of a base. Whenever we add those two compounds together, we then again take solution total. So even if you just want to write down like the idea of what's happening, like acid-base reaction, put mass total, that means the solution of the acid plus the solution of the base to give you your mass. Many times these are also diluted, like 0.1 molar solutions or 0.5, 1 molar solutions. They're still fairly dilute, so that's why we then are allowed to use a C of water, which is usually given to in the problem. It says like assume this is still a specific heat capacity of water, and including CAT, which is our calorimeter. This is assuming we always know the heat capacity. We always will not though, so that's sometimes an omission. You won't have to use that itself. So there's a special situation with reactions. So like this is a true reaction, right? Acids plus bases will react. So sometimes you'll have equivalent or so equimolar conditions. What's equimolar mean? Same moles, and if it's in the same mole ratio, then they're both going to wipe out 100% at the same time, meaning that they're both the limiting reagent. But if you don't have that situation, if you don't have equimolar conditions, let's say you have the sodium hydroxide is like the base or something. Let's say you have the sodium hydroxide in a limiting capacity, so it's limiting reagent. When I'm finding the delta H at the end, I take the Q because there's only so much heat that's going to be absorbed or released in this process. And who determines how much is absorbed or released? If you, say again? The limiting reagent, right? So the one that's going to halt the process is going to stop the heat from it being evolved. So that's why we have to divide by the moles of the limiting reagent if that's the scenario. We don't always see that, but sometimes you do, and I just don't want you to make a misstep on that. And so scenario 1 is just salt and water, just making a solution. Step 2 is a true reaction between two aqueous solutions, which a lot of times that's going to be an acid-base reaction. And then the last one is whenever you have a physical process. Actually, no, sorry, this is still chemical. So this is like a metal, can you guys think of a metal plus acid reaction? So the lab you did, right? So magnesium plus HCl makes what? Makes magnesium chloride of herd and what? Hydrogen gas, right? Well, that's a chemical process, and what we would assume is the solid magnesium and the HCl would react, but initially they're physically combined because one's a solid and one's a liquid. They're not chemically combined until they start to react. So the general rule of thumb, which I don't exactly like, but this is how they kind of want us to teach it now. They changed this like the last 5 years. They want you to take the mass of the HCl solution, which will be the acid in this case, and the water's specific heat capacity, because remember C is kind of going to be the whole solution as a whole, and this water is more, or the specific heat of water is closer to the specific heat capacity of HCl, not magnesium. What's magnesium's specific heat capacity generally? It's a metal. Super low, right? Not even close to that of water. So remember, our mass and our specific heat capacity have to be somewhat congruent in what we're comparing. So we would take the mass of HCl or the acid and then still do the Q-cal if we had it. But assuming that our limiting reagent, which this was the case in our gas evolution lab, assuming that the limiting reagent is still the solid, we can still take the solid into account, but at the end, by dividing by the moles of the solid that reacted. Okay, so these are some rules of thumb. I just wanted to give this to you up front because I know we're going to be using this, maybe not today, but more on some more problem sets. Okay. All right, I will finish answering questions on enthalpy problem set at the end of class. I didn't get to 2 pieces on Friday, Hess's law and bond association energy, and I have to do that today because I won't be here Thursday this week. Okay, ready for these? Questions? Who went to bed before midnight? Good Lord, guys, what in the world? These are insane. Okay. I did have some of this printed for you. If you want to pull back out your packet, I think it's going to be like the second page. Why are we going to bed after midnight? Like, what's the deal? Saturday. What happened Saturday?
Then you don't sleep, and then everything's messed up.
I don't understand. You only gained an hour. You gained an hour. Just 1 hour, I know, but, you know. I don't really want to know what time, but eventually I'll do a sleep study, and I always do a sleep study in AP Chem, but it'll be like February, okay? And you're required to track your sleep patterns for me.
Yeah, I'm gonna do so well. Yeah, so did I.
Why? Doesn't make any sense. Okay. All right, so here we go. Who's got this out for me? Yes? I know you're really like on no energy, I understand, but you got to respond. You have this out. Okay, well, some of us do. I'm moving on. All right, so you have 3 ways to calculate delta H of reaction, or delta H of solution, or delta H of combustion, whatever it may be. Reaction is the general term that we'll use. So we already know how to do the first one, which we remember Q can be achieved in many ways, but Q is equal to MCAT is probably our most convenient way to find it. If you're trying to get from Q to delta H, don't forget you just have to divide by moles and you got it, okay? So check, we already know how to do this. We really do. The idea, though, is that we sometimes don't have data, so we don't have mass, we don't have delta T, so there must be another way to find delta H of reaction. And that's going to be either Hess's law, which is an indirect fashion, or bond association energy. So there are 2 ways to do Hess's law. So Hess's law is the bomb because it's really easy. So what we have to consider is that we will be given standard enthalpy of formation values in a table, What's standard enthalpy of formation look like, symbol-wise? Not just F, delta H, not F, okay? I know the terminology and the symbols kind of get confusing, so make sure you're defining that. Okay, so we can do an indirect assessment of the delta H of reaction by this big mama equation is how it's phrased in your MSI reading. So it's delta H of reaction is equivalent to, what's this mean? The sum, so sigma is sum of the moles of the products, delta H of formations, minus the sum of the moles of the reactants, delta H of formations. And anytime you have a table and you have all these standard enthalpy formations given to you, they likely will not give you the enthalpy formations of any single elements. Okay, so they won't give you any single elements because they want you to know that free elements are 0 kilojoules per mole, meaning they don't have a standard enthalpy of formation. So this one's pretty simple. We have to have values though. So what we're going to look at is this table below. So I'm going to scroll up for you guys. I'm going to set it up first without numbers to show you what's happening, and then we're going to plug the numbers in. So you would absolutely get a calculator on this because the math can get a little bit rough. And you'd have, if you guys have your reference table out, on the back of the reference table in the thermochemistry section, you'll see this equation given to you. So this is given on your reference table. Okay. All right. So I have to do products minus reactants, right? So who are the? Give me one of the products, Marcus. Okay. So I'm going to say delta H of reaction is equal to the sum, and I'm just going to put all this in brackets so I know that this has to be added together. The sum of 4 H of formations of nitrogen dioxide. So I know I'm going to plug in H of formation in here where I put NO2, plus 6, and these gases and liquid states are actually really important, so we'll make sure we look at the right one down below, plus 6 H of formation values for water, liquid. So all this needs to be added together because this is a sum, right? This is this right here. And then we're going to subtract the sum of the delta H of reactants. So I'm plugging in for N the coefficients since those are the mole ratios. So Christian, give me one of the reactants.
4 H
And H3, right? Ammonia. And that's gaseous. And we're going to add that those 4 ammonias, delta H of formation values, to 7 O2s, or 7 oxygens. Yes. So this is the delta H of formation of nitrogen dioxide gas. This is the delta H of formation of water. This is the delta H of formation of ammonia, and this is the delta H of formation of oxygen. We already know one of these. Which one is it? Oxygen is going to be what? But you have to write it. You actually get a point for writing 0. Just an easy point, right? Okay, so now what we're going to do is we're going to look below, look for nitrogen dioxide. You guys see it? See it here? Okay, so plug in positive 33 where you put nitrogen dioxide. And I'm going to write this alongside with you guys. Delta H of reactions equals to 4 times 33 kilojoules per mole plus water liquid negative 286, right? Sorry, it's a little blurry. So it's 6 times negative 286 kilojoules per mole. Can somebody sum that for me real fast? Calculator action here. Okay. And this is still kilojoules per mole technically, but we're good here, okay? So this is the energy of the products total. We're going to subtract the energy of the reactant. So subtract the enthalpy of formation of the reactants. So that's 4 times ammonia, which is ammonia gas, right? So negative 46 kilojoules per mole plus 7 times 0. Include the 0 because then it represents that you've done something in relationship to oxygen. So we're going to subtract a negative, what? 161. Oh yeah, 81. And that's kilojoules per mole again. Okay, so we have our energy of the products minusing or subtracting the energy of the reactants, both of which are negative. So then in the end, what do we get for our delta H of reaction? 4,000, no, sorry, negative what?
1,400.
That's it, 400, I'm sorry, I think something else. Kilojoules per mole. So this should be our final. So overall, this whole reaction process is exothermic. What would happen to the temperature? It would go up because it's releasing energy to the surroundings, which the thermometer is part of the surroundings. Okay, so it sounds like, okay, we're kind of plugging a lot of numbers in, but if you stay organized and you keep your initial general reaction first, plug your numbers in, and then make sure you're really clear when you're subtracting and adding, you guys can do that, okay? So I have another one for you guys. Ready? I think I have another one. Oh, this is just a sample of what it looks like in your textbook. It'll say like delta H formation. It has everything listed here with the states of matter because they do matter. And then there's another one right here. I mean, they go on and on and on. So there's a lot of data there for you. Okay, so I have this enthalpy table for you. Notice I have happy phased out the sucrose. This is what you're going to be finding. So I want you to find the delta H comb, which is delta H combustion. I'm sorry, I'm telling you the delta H of combustion for sucrose, and I'm telling you that value is negative 5,644 kilojoules per mole. I want you to find the delta H of formation for sucrose. So think with the person next to you on how you want to start this. Notice how is my reaction written out here? Okay, it's not written out, but how should it be written out? As a what reaction, Kaz? Combustion reaction. I heard heat of formation. Not a heat of formation problem. It's a combustion reaction. Margaret, who's reading? Oh, no. Yeah, I did that wrong. I was trying to add my 11s. Release the pop energy is going to be present. All right, I'm going to leave these values up here for you. Tell me what values you need. I can read them off. Yeah. Yeah, water is likely going to vaporize under conditions like this, like very, very high combustion reactions, hot combustion reactions. All right, so I know you guys are solving for delta H of sucrose. What does that mean you have to set up? Like, where is delta H of sucrose going to appear in this equation?
reactants.
And the reactants, right? So you're going to plug and put that as X as one of the reactants, and then we'll solve for it. So before you set up all the way, let's gather the data you need. So what do you need from me up here? Carbon dioxide is negative 103.85 kilojoules per mole. So negative 103.85 kilojoules per mole. And what else do you need? Water gas, right? Water vapor. And that's going to be negative 241.8 kilojoules per mole. Get those values? Can I scroll away from this? Notice I did not give you oxygen, and the table doesn't either because it's 0. It's a free element. Products and instructions. So the products here. Here. That's just how I see the definition of that equation. I flipped my sums at the end, but can I get a thumbs up if you're approximately close? Yes. So if you had, and I flipped my sums at the end, but if you had your setup the same as mine, negative 39 and some change, minus x is equal to this negative, then when you added your H products to both sides, this is still going to be negative 1700. Since you have negative over here, though, you should flip your sign. So I divided by negative 1 at the end, which will give me a positive value. And that's the only thing that makes sense because you have a negative value minus a positive value to give you a more negative value. Yeah.
If negative 5,644 kilojoules is the entire reaction chain, so it checks everything, what is like one value?
What does one value mean? It means the energy that is either released or absorbed when you form 1 mole of that substance from its elements.
No, you like the answer. What's that?
Oh, this value? That's what I just said. Melting agent formation, right? we solve for delta formation of sucrose. So this right here means sucrose, 12H22O11, right? Solid. It means the energy it takes to do this. 12 carbons plus 11 hydrogen gases, diatomic plus 11 halves oxygen. Is that right? Yeah. So carbon plus hydrogen plus oxygen yields sucrose. So this is the delta H formation value that we just solved for up here.
We did that through like, enthalpy of combustion.
Which is the same as that enthalpy of reaction. Enthalpy of reaction is just a really generic term, but this is specifically enthalpy of combustion because we combusted this specific reactant.
So you could do it either way.
Well, so this reaction, delta H formation, would have to be given to you in a textbook, in a table. If you don't have the table, or like I scratched out that value, you'd have to do it from different data. Well, the different data you have is all based on this combustion reaction right here, this combustion reaction. Because they posed it in the frame of combustion, then you have to pull data about each of these individual reactions and products and do the Big Mom equation, delta H is equal to H products minus H reactants. So whatever data is given to you drives how you solve the problem. Okay, that's what we're talking about solving for delta H in 3 different ways. Okay, thumbs up if you can do this. Given data, right? You can plug it in, calculate. Okay. So there's, let me show you this first. I have this up here twice, but forgive me. You guys have this on your paper? Something like it. It's another indirect fashion of solving for delta H. It still is called Hess's law. I like to call this first one here, oops, Hess's law. Like this right here, blue stuff right here is Hess's law, but it's Hess's law in reference of products minus reactants. The other form of Hess's law is summation of reactions. So if you want to write down that as Hess's law, summation of reactions, we're going to take many reactions, like 4 to 5 reactions, and we're going to add all the reactions up. But this one's kind of fun because it's actually kind of like a puzzle. So here are the steps, which I think I've written this out for you as well. Yes, okay. So for the summation, what we'll do is we'll take a series of reactions or a series of equations, and we'll add all the reactions up. All those reactions will also have a delta H given to us. So these equations will have a delta H of reaction given to us. As we add up the equations, we're also adding up the delta H of reactions, and at the end, we solve for the final delta H, which gives us that reaction that we kind of, I call our target equation. But in terms of, how do we know what to add up and how do we know if our reaction's right, we actually have to take a second and flip reactions. When we flip them, we change the delta H. Any way we manipulate a reaction, like for example, reversing a reaction, we do the exact same thing to the delta H. So if I reverse a reaction, I'm then going to change the sign on the delta H. So if it was a positive, then I'm going to make it a negative. If I multiply the reaction to get to a certain number of reactants and a certain number of products, that multiplier is not only applied to the reaction, but also to the delta H. After you do all your manipulating of the reactions, which I'll show you how to do this in a second, you just simply add up the reactions, or the equations, and then you alter the delta, or you add up the delta H at the end, the way you have altered them. So not just what you had initially, but if you change the sign or multiply by 2 or something like that, then you need to include those in your summation process. So right now this is like gibberish, but we're going to take reactions, we're going to flip them around, we're going to add them up. That's it, okay? So this is like a puzzle. I feel like jigsaw puzzles. Thanks, Taz. Okay. This is the same thing. Okay, this is the first reaction I'll do with you, okay? So basically the boldened reaction up there, 2 B solids plus 3 hydrogen gases yields diboron hexahydride. We need to solve for its delta H reaction, or its delta H. But we have to do that from these 3 given reactions. We must use all of them. So the way I like to start is I like to write my target equation at the bottom. So just give me a second, let me write that down here. Leave some space and write your target equation at the bottom. 2B. So we're going to take these 3 reactions and rearrange them to solve for this final reaction. I like to add the knots, but it wasn't there, so I'm just going to add them all the way. Okay. So what do you guys see in terms of the reactants that I want at the very end? What two reactants do I want at the end? I want boron and hydrogen, right? Where do you see boron and hydrogen up here? In the first reaction, okay? So let's just look at boron for now. I want 2 borons at the end, right? How many borons are in this reaction? 2. So I'm actually going to keep that exactly the way it is, because what's going to happen is this boron is going to follow me all the way down, because I will never cancel it out, which means it's going to stay with me at the end of the reaction. So just write this reaction out again for me. 2B solid plus 3/2 O2 gas yield B2O3 solid. Delta H is negative -1273 kilojoules per mole. Okay, so I know I want these 2 borons to stay with me, because what we're going to do is when I start adding second and third reactions, what's on the reactant side and the product side, if it's exactly the same, I can cancel them out. Just like spectator ions with NIEs. If something's in the reactants and the products, they're exactly the same, we can cancel them out. So I have 2 borons I'm keeping. Do I want these 3 O2s at the end? No, so I'm actually going to, or the 3/2 O2. I know I'm going to have to cancel out some oxygens eventually. So I look ahead, I see oxygen in 2 equations. I see it in this equation and this equation. So I'm going to hold off on that one just for a minute, because I'm just not quite sure which equation is going to help me cancel out those oxygens. But do I want the 2 BO3s at the end? Yay or nay? Nay. Okay, so I do not want those. So I have to find a way to cancel this with something on the reactant side. So which of these equations has that in it? The second one, right? So I want to write this second equation either exactly as it is, or I can flip it, meaning inverse it. What do you guys think I need to do? Inverse it, right? So this 2B, or B2O3 solid, okay, plus 3 liquid waters yields, so I flipped it, so I'm actually writing the reactants down now. B2H6 gas plus 3 O2. And so since I have flipped this reaction, I'm going to flip the sign. So this is not going to be negative 2O3. The delta H is going to be positive 2O3. So the sign must be flipped when we flip a manipulate a reaction. Okay, so successful. I can see the B2O3 and this B2O3 here are going to cancel. I'm just going to wait to cancel them at the end though. I also see that I have B2H6 in the products, right? Now I want them at the end, so I'm in good shape. Now I see the oxygens here and the oxygens here, so I'm looking good. I can't cancel them all the way yet because I have 3/2 and I have 3, but I might at the end. Okay. Okay. So what else do I need in the reactants at the end? Hydrogen gas, right? So it's obviously it's in the third reaction here. How many of them do I need? 3 of them, right? Are there 3 here? No. So I'm going to now apply a coefficient and manipulate this equation by multiplying the entire thing by what? 3. If I multiply the reaction by 3, I also multiply the delta H by 3. Okay? So I'm going to put 3 times H2 gas plus 1/2 O2 gas yields H2O liquid, and this delta H is 3 times a negative 286. Can I move on to the simplification process now? Okay. So I have to maintain, like, I need everything that I don't cancel in the final reaction. So I'm just going to circle those to make sure I'm here first. So I've got 2 B's right here. Okay, so I've got that settled. I have 3 times 1, so that's 3 H2s in the reactant side, so I'm good there. And then I have the B2H6 in the product side. So I can see that they're all here. Now I need to verify everything I did not circle will cancel. So do the 2 BO3s cancel? Yes, there's 1 here, there's 1 here, they cancel. So 1 in reactants, 1 in products. Do the 3 waters cancel? Yes, there's 3 waters here, and there's 3 coefficient applies all the way through. So there's technically 3 waters here, so this will cancel. And then how many oxygens are on the reactant side? 3 total, right? Because there's 3/2 here, and there's 3/2 here because the 3 distributes over. So there's 3 oxygens here, and then there's also these 3 oxygens here. So all the oxygens, boom, 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 will cancel. So I've successfully added up my my equations to make my final equation. Now I need to add up my delta H's. So negative 1273 plus 203 plus 3 times a negative 286. Anybody? 1928. So this is the delta H. I added standard, but this is the delta H reaction for this equation. So this is yet another indirect way of finding delta H, and this is indirect because we're not physically manipulating the materials and measuring their heat of reactions and then dividing by moles. That first, like Q over moles, are direct way. This is an indirect way of using equations. So far, so good, guys? Yeah.
Are like the equations always going to be different?
Yes. Yes. Okay, we're going to do another one like this. Ready? Okay. So, who want to do this one? Hold on. There's one more I actually want to do with you. Oh, actually, hold on. Go to your, do me a favor, pull out your Hess's Law problem set. It's like right next to the Enthalpy one. Let's just do one of those and then we'll come back and do the rest of the ones here. So it's just a Hess's Law. I give you an example. I might be lying. It might be one page back. So, if I remember the page, it's on the back of the page, it's called Hess's Law. The very first one says, yeah, so enthalpy is a state function. So go on to the student practice where it says student practice, blah, 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 and number 2. Actually, I have to pull up that. I know I have it here. Yes, I have it. Just wait for that. You guys try that one while I get on my notes here. This is like really messed up. If you're good, done, go ahead and do the next one. I'm just going to let everybody choose to ask a question. Which one? So this is my part. This is my part, right? I want this exactly. So my first equation's got 2. It's like, I want this. Oh, it was me. So I want this. flip it to make it negative. What's that now? You doing okay? Okay, so finish the one you're on right now, and we're going to talk about the last concept. Okay. And if you're feeling dangerous, go ahead and do number 6. Maybe we can do that one. Wait, I'll let you start number 6. If you're feeling dangerous. Okay. Go take a couple more minutes and get your stretch breaking on with them. You're good. Okay. Makes sense, actually. Not on my smart display. States of matter matter. States of matter matter. Add your states of matter. Because they matter. Wait, why? I'm not hearing. And everyone's like,
I feel like if it's cold to mess with this,
It's fun. It's like a little jigsaw.
In chemistry, it's just solving
How much guys do they?
This is the fun part of our
Hey guys.
So like the whole thing cancels out and stays.
Alright guys, like take one more minute and then we have to do our last set. You need to get the number 6. No, it's just saying solve for the H reaction. It just gives you the specific reaction of neutralization. I'm recalculating number 6. Margaret, I just got 203 again. Did you get 203? Okay, so I've done this 2 times, and I got, I'm actually going to recalculate again. I got 203, I got negative 54, and I got the very, very first time negative 340, so just going to recalculate. Alright, so go back and reassess number 6 on your own time. We're going to do our last set. We'll check, it says 19 here, but number 6 tomorrow, or maybe during intervention. Okay, so let's look back up here for me. I know it's like a puzzle and you can't stop it. You just have to be strong. Okay. Everybody look at my enthalpy diagram. Do you see my enthalpy diagram? Caw up here. Okay. So enthalpy diagram. You can do the same thing with Hess's law, but you'll notice that you don't really have to cancel reactions because it's already kind of telling you everything is negating down or coming down to the same, whatever this is, liquid water that we're forming from these 2 individual elements. So if the total delta H is negative 286, and this little bit here is negative 44, what is this? If the total is negative 286, this little bit here is negative 44, what should this be? Negative what? So you're taking negative 286 equals negative 44 plus x. So this is x. This is negative 242, and this is kilojoules per mole. Okay? So you can still solve this from a pictorial diagram too. Okay? All right, so a couple more just images, and then we're going to go into the last piece. So when you're looking at, let me go back to that picture in a second. So when you're looking at this, who's ever seen these? Okay, we've seen these in our math class. Everybody's raising their hand. Like last week, not like honors camp. You saw this last week. If you had this as your reactants, and then these are as your products, is this an endo or exo process? Okay, louder and prouder, because I'm increasing the amount of energy in the products. Where's the enthalpy of reaction? 1, 2, 3, 4, 5, 6. Where's the enthalpy of reaction? 4. Because it's the difference between the delta H of products, and here's your delta H of reactants. So when you subtract products minus reactants, you get the difference there, and this is delta H reaction. Okay? This is the Big Mama equation, delta H reactants equals products minus reactants. Yeah. Activation energy is actually number 1. So activation energy goes from where the reactants began all the way to their peak. So that's why it's not this piece, it's number 1. This is EA. Good question. We're going to get to that shortly. Okay. So back here, I think you got it now. Never mind. We're moving on. All right. So this is the last part. This is the delta H. I'm sorry. This is our third way to solve for delta H, which is our bond dissociation energy. BDE, bond dissociation energy. This one is, I'm pretty sure, maybe not in your notes. This is well, not the notes. Where it says 3 use bond dissociation energy. That's it. And then when you're writing down, I want you to call out the main difference you're seeing about this reaction. About this equation. What? Reactants times products. So you have to memorize which is which. So delta H of formation values. When you have delta H of formation values, you have to do products minus reactants. When you're using bonds or bond dissociation energy, you have to do reactants minus products. So big note to self. Just make sure you star those so you see that there's a difference there. And so this one is actually in alpha order. I don't know if that matters at all. Bonds broken minus bonds formed. Oops, bonds formed. Or that's an alpha. This is not actually. Broken minus formed is an alpha. Let's have to do the alphabet real fast. All right, so everybody turn to your partner. Okay, one person's going to be a bond. One person's going to be a bond. And one person's going to be the bond breaker. Okay, so break the bond. Break the bond. Hiya! Come on, break the bond. Okay, jeez. I got some more, JT. Okay, so, bond breakers. Did you put energy into that process or take it out of that process? So breaking bonds is an endothermic process, right? Okay, and then now I want everybody, you guys watch I Dream of Jeannie?
What?
Okay, that's pretty old. Okay, so now everybody form a bond. You have to release, okay, you guys can do it, okay. Okay, so we released what? We're satisfied with ourselves. Okay, so we have released energy. So bond formation is technically an exothermic process, so it's technically negative. So how do I get away with this equation? It's actually every single bond dissociation energy, so BDE, bond dissociation energy, every single one published in a textbook is positive. Because every single bond dissociation, so cracking a bond open, requires energy. So how do I account for that formation being negative? How do I calculate this? I subtract. That's it. Okay, so that's how I'm getting away with all the bond dissociation energies themselves being positive. So technically this value is positive and this value is positive. It's just the negative sign is giving us the fact that it's an exothermic formation process. Okay, so we actually have to draw these Lewis structures out. So go ahead and draw H2 for me. We have to draw these Lewis structures. The dot structures, structural formulas. All right, guys, 2 H's attached to each other. 2 H's attached to each other. What I'm going to give you is I'll give you the structures, but I'm going to ask for you to try a little harder the very first time, if that's okay. So, H2, give me 2 H's. And they're bonded together with
A bond.
a bond. Okay, great. Okay, ooh, what's C2H2? Name it. Whoa, no dyes. This is organic.
Oh, yeah.
Ethene, and that's going to be carbon to carbon connected with a
Double bond.
no.
Triple bond.
Triple bond. Oh, sorry, you said ethene. You meant ethine, right?
Yeah.
Okay. Sorry, I like to agree. Ethane, ethene, ethine. Sorry, so this is going to be C, H, H, and then what goes in the middle? A triple bond. Okay, so the bonds are the pieces that matter. All right, so we have H2 plus ethine yields, what do I need here? This is what? Ethane, so what do I need in the between the carbons? A single bond. So this is going to form C to C, and then everybody gets octane. You get octane, you get octane. Okay. All right, so so is this balanced? I did not check. Oh, dang it. Okay. So there's a 2 on the H here. So how many H's do I have? How many diatomics do I have? 2. Okay, so let's draw another one here so we have them all clear. Okay, so I need to account for all the bonds I need to break in this process. So how many bonds, or what bonds do I need to break in this process? Because I'm gonna break them all, and I'm gonna let them rearrange themselves into forming this. So let me go in order. What do I have to break first? How many hydrogen bonds? Okay, so there's one here, so that's 2 H bonds. So just write 2 H bonded to H bonds. Okay, so check, count for those. I also need to break what from this structure? So, okay, so I'm going to break a carbon triple bond, just one of those. Check. What else do I need to break? 2 carbon to hydrogen bonds, okay? So I'm going to add 2 CH bonds. All right, is that all the bonds broken? Yes, it is. So bracket those so you know that these are bonds broken. All of these are bonds broken. Okay, what bonds are we forming? Sorry, this is a little sloppy here. I'm forming what? 6 what? So 1, 2, 3, 4, 5, 6, 6, 8 C to H bonds. Okay, so we're forming, I'm just going to write them on the bottom line here. I'm forming 6 C to H bonds. And what? 1 single carbon bond. All right, so what I have in blue up here is all the reactant bonds I'm breaking, subtracting all the product bonds I'm forming. Okay, so I need data for that, right? So what do you need from me? All the bond association energies, right? Okay, so we're doing the summation of bonds broken minus the summation of bonds formed. Here's our 2 H's, triple bond, 2 carbon hydrogen bonds, 6 carbon hydrogen bonds, and a carbon single bond. And the values for these are published in that table as well. So it's 432 for the H bond, 839, and this is all in kilojoules per mole, for the triple carbon bond. Notice that's a really big value, right? Right, triple bonds are super what? Super strong, right? They've 3 layers of defense, so you can't break it really easily. And then the 2 carbon to hydrogen bonds that's a 413 for just the single carbon hydrogen bond. We're multiplying that by 2. So there's that one. Here's the carbon triple bond. Here's the carbon hydrogen bond. And then we're subtracting bonds formed. So that's 347 for the carbon-carbon bond. And then 6 times, again, 413, which is our C to H bond. So I do have the value for you here, but summated all of these together, all the bonds broken was 2,529 kilojoules per mole. So this is the energy it takes to break bonds. And then this is the energy that's released when the bonds are formed. I'm having you predict before you start calculating. So I put in this amount of energy to break bonds. I released, technically, this amount of energy to form the bonds. Overall is this endo-exo. exo, because obviously you can see this is a bigger number, right? But it's a bigger number because it released more energy. So what, one second, Cassie. So what happened here is all of these bonds initially had a lot of pent up energy. And when they formed the ethane, they were more stable. More stable, like if you were more stable, you're kind of low energy, you're kind of chilling, right? This is low energy and kind of chilling. It released all its pent up energy, so it's not stressed anymore. Question, Cassie. Two, 8, 2, 5. That's okay. So yeah, this is the bond broken energy. So that's that value there, and then this is the bond formed energy, which is here. Okay. So overall, yes, it's exothermic. All right. One more like this. You just gotta draw some structures. Ready? What? Yeah. What can't be negative? No, I said it certainly is negative. Well, no, not always. Yeah, so this is an exothermic process, so it's a negative value. If it's an endothermic process, it's a positive value. No, I said the BDE values. Okay, so the energy that's associated with this, and this, and this, and this, and this, these are all positive, 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 positive. Yes, so the BDE, bond association energy values are always positive, okay? All right, one more for you. Oh, let me show you this first. This is what your data table looks like in your textbook. You see? They're all what, Darcy? They're all positive because every single one of those come with the karate chop, so breaking that bond into 2 pieces. All right, so, answer these for me before we go. Bond breaking is A, B, or C? B, thank you. Bond forming is exothermic, and this is my heartbreaking example. So diatomic or diatomic nitrogens together in a triple bond, and then they broke up. It's depressing, but it's really hard to do. But it's a positive value, so it took some energy to do that. And then they got back together because they were like, I can't live without you. And they released energy. And so this is a happy couple that's kind of calm and stable. They've got their no student loans, house paid off, whatever. They're good. And this is the one they're struggling, but they're gonna make it because they got back together. They couldn't live apart. Okay. Okay. This is the one I want you to do. No, I just did that. No, I just did this one. Do this one for me. I have values on the back page. I'm going to come right back to that. So draw your structures first. I don't know why I put them all on the same page. Is it balanced? Is it balanced? Yeah. Yes. Okay. Notice I gave you the structural format so that you could then expand upon that, right? All right. I'm going back to the BDE table in 3 seconds. Ready? I hear Thanks. Okay. So the ones with the data tables are usually everybody's favorite because it pretty much tells you what you have to do. You just have to remember which direction to go with it. Bonds broken minus bonds formed.
Why do some of them have an A as an axis? An A as an axis.
I'll tell you that in a second.
Where do you see the A value? Oh, it's in here. Does it matter the order? Whether it's H, C, or C?
Okay.
It just depends on how the table's written. All right, good questions while you guys are wrapping up that. One, you'll notice it doesn't matter how it's written. It's H to C or C to H. It's just however the data table is written for you in particular. And then on this value or on these values given in this particular table, they tell you that all of these are exact values as an A. It's because, I don't know if you guys see the title to this table. What's it say? Average, right? So in different scenarios, like double bonds and triple bonds can be shorter or longer in a given molecule themselves. So if the bonds are situational, meaning in different conditions given, then we actually have to take each of their independent bond association energies and we average the values so we can put them on a table. So these are still averaged, which is why the doubles and triple bonds are the ones where it says we'll discuss multiple covalent bonds in section blah blah blah. It's because these are still averages, they're not exact because they do vary based on the situation that they're put in. Yeah.
Why sound like dashes?
Because I don't know. In this particular table, I don't know why there's dashes. Probably because many times this forms a resonance structure, and they form it's like a 1.5 bond length, and it's an average. They do publish this value, but they don't publish this one. It's something called resonance structure. We'll get into in like March. Okay. All right. So I have like 7 or 8 minutes left with you guys. Okay. So here's what I'm looking for. In terms, I might drop one of these things. We're not going to do our lab on Wednesday because I don't think we have time. So I'm scratching this lab thing. You guys have your Hess law problems set in front of you, right? 1 through 6. We've already got like 2 of them. Perfect. So not too much more on the jigsaw puzzles. And then I don't have any more, like problem set wise, I don't have any more bond association energy problem sets, but I did have some good ones from the textbook. So that's what these are right here. So page 420, 82, 83, 84, and 106. 82, 83, 84, and 106. So there's 4 there, plus maybe 4 or 5 left on your test and stuff. So that would be 9 problems. I will go over PS and enthalpy during intervention shortly. Okay? I don't have to use it for everything yet, but I can. Remember, guys, I have to adjust my keys sometimes year to year. I haven't scanned the enthalpy one in like 2 years. I will scan this. While you guys are working, I'm passing out gases tests so we can talk about these in intervention, okay? So please work. Please work. Okay, I'm sorry, but I'm gonna be lazy. I'll call your name. Okay, I'm calling your name. Now, okay, there's gonna be like 3 pieces of paper.
You did.
What was the question? Do you have a question?
Yeah, I can put him in.
I think it's just pick like whatever the closest to minus. Whatever the water.
See how much?
Somebody just took Miriam. Bring it back. Bring it back.
Okay, response? Oh yeah, I got 2,000% there.
That was the easiest exercise ever.
Andrew.
Funny how I wrote the days to them after I did the right now. All right.
Yeah.
No, I was so proud of this work. It was so neat. I was like, wow. I wrote some eight exams.
Tied up 30. That's what I got. And then I got
No name again. Oh, come on,
Oh, she added that.
Oh, I just.
She drew an angry face, just like, why? Because I got 2,000% in it. I don't know what to do.
I got a yes. You got a yes.
Oh, no names. I'm telling you.
I'll see what I got. I don't know. I still got 7 out of 10.
Oh, you did not.
Yeah.
I can only got 4 out of 10.
I want to try to
I just do go for
I did a lot of study hours.
Alright, guys, listen. You do not take one piece of paper and then come look at one you can scratch one to your house.
That's a lot. Not even. So I'd say anything above 40. Either well.
If you did not take multiple worksheet, come grab one now. We left.
I got a 60.
Did you put your docs?
Just 2. I know that
I don't know the I have And then I did and then I did the problem thing on the back. But I did all the tests.
All the documents. Percy. No. Oh, yeah. Oh, let me show you that. Here you go. 3, 2, 1, listen. So I went back, number 4, I had it wrong on my key, but I went back and made everybody got it right. So number 4, pull the straight.
And then number 10 and 20, where I talked to some folks and they said it was unclear what a division symbol was. So I went back and gave credit for my ambiguous slash, which is a division symbol. I did not want to do that, but I did it. And then the last question, 20, which was diatomic. I didn't state it was diatomic, so theoretically you could have assumed it was monatomic, which meant you would have had the single dots versus the double with the diatomic dots. So I went back and gave credit.
Well, what are we doing about that? Are we actually gonna like continue or we can have my intervention? I think it should be fine. I don't remember. I'm representing information. Yeah. I think my question was subtracting the big pressure. I was like,
The rest of it was okay. I just don't have any good rest left.
that one's forever.
Basically.
It's alright. It's only a quarter. Is that what you
I think I do that.
That was me last year.
I know, man. I remember that. All right, so can I get you like I'll call you back. What's your third?
Third period, Barbie.
Okay, can do. Bye. I'll call you back.
Your tests are really good. They really are.
I think you had a bad day.
I'm putting in the work. It's just not. It's not displaying.
It's displaying a little bit. Tell me, like, just trust me. The tests are just hard. That's just how AP tests are. But you'll be fine. Just keep.
Have like anything like you know how we did the mold day? That was kind of like an easy test.
I kind of do that already, which is your multi project from
Yeah.
first quarter, and then you have your good people points, right?
Yeah.
That's a free test grade. It's a 100 test grade. 10 hours
Oh, that's
tutoring,
right. Yeah, yeah.
and then I do the same thing in spring.
Okay.
So that's what I always try to help
I
out.
have like another kind of 300.
Yeah,
I think there's that really helps.
I always try to help out. You're good. Bye.
Bye.
All right, dude. You want some tape? There you go. Oh, I forgot to